Good morning, everybody. So today we touch upon the very last topic of the course, which is actually a new introduction for this year because I've never managed to finish all the other topics so fast. Thanks to my tendon inflammation, I was faster because I didn't have to write. And so we have this extra lesson where we can cover policy gradient methods, which typically I couldn't do. So this is the schedule for today. You'll notice that the style of the slide is different because I had to prepare these slides especially for today. And since I knew I was not going to write them down, well, I used LaTeX to write it. So everything we have seen so far in terms of reinforcement learning were value-based methods. So in these methods, we were always learning either both a Q function and a policy function, or we were learning just a Q function, so an action value function. And then the policy was computed implicitly from the action value function. So the presence of the action value function was really fundamental in the method we have seen so far. And that's why they're called value-based methods, because they rely on the learning of a value function, an action value function to be more precise. What we're going to discuss today instead is a completely different class of reinforcement learning methods, which are called policy-based methods. And that they rely on the policy gradient theorem. That's why they're also called policy gradient methods. And here, the idea is that we don't learn the action value function. We directly learn the policy, which makes a lot of sense if you think about it, because in the end, our final goal has always been to learn the policy. So the action value function was just an intermediate goal through which we could then learn the policy later. And policy gradient methods, they do exactly that. So you parametrize a policy, typically using a neural network, but again, you can do any functional approximation techniques that you want. So you're going to have your policy, which depends on the parameter theta, and you try to find the value of theta so that the policy performs well for the system you're trying to control. That's the key idea. I think it's a very straightforward idea. It actually makes more sense than everything we have done so far. It's simpler, it's directed optimizing what we care about, which is this cost J of theta. The optimization is going to rely, as usual, on some variance of gradient descent. For the same reason we have relied on stochastic gradient descent for training the neural network representing the value function. Here we do the same because it's going to be, in general, a big neural network with many parameters theta. And so using second order optimization like Newton's method does not scale. So a key advantage of switching from value-based to policy-based methods is that now we can tackle continuous action spaces, because our neural network is going to output a continuous action. Well, it could also output a discrete action if you want to, but you can use it to output continuous actions. So that goes very well with robotics, because robots do have a continuous action space, which is typically the joint torques or the joint velocities. And also, in general, policy gradient methods, they rely on stochastic policies. So even if in the end what you want to learn is a deterministic policy, during training, you let your policy be stochastic, which helps in many aspects. It helps for exploration, and it helps also for smoothing, So simplifying a bit the problem that you're working with, because if your policy is stochastic, that creates a sort of smoothing effect over the dynamics and the cost, which may be non-smooth. But having the policy that is stochastic smoothes out the discontinuities in the cost and the dynamics. So a very common choice for the stochastic policy is to use a Gaussian probability function. So you simply parameterize the probability of taking the action u when you're in state x as being proportional to this exponential function. And that's exactly the probability density function of a Gaussian. So here you have the value of the action minus the mean of the distribution squared divided by the variance, two times the variance. So in this case, the parameter theta could be split into two parts, a part which is used for learning the mean of the distribution, and another part for learning the standard deviation. So it's as if you had like two neural networks. One network outputs the mean, and that network depends on these parameters theta mu, and the second network outputs the variance, and that depends on the parameters theta sigma. By the way, the slides should be on the shared folder on Google Drive if you want to open them. Of course, you could use other kind of probability density function, but the Gaussian, as usual, is the most commonly used. So why should we optimize the policy? Well, the main reason, or one of the main reasons, is this ability to handle continuous action spaces, which for robotic systems work very well. If instead we look back at what we were doing with value-based methods, in value-based methods, since your key objective is to learn the action value function Q, then to figure out what action you should apply, you need to solve this minimization problem. You need to find the action that minimizes the Q function. And in everything we have seen, that was not an issue because the action space was discrete. And so this minimization boiled down to simply evaluating the action value function for all the actions. If you have, I don't know, 100 possible actions, you just evaluate Q 100 times, and then you keep track of the minimum value. And that tells you what is the optimal action. But if now U is continuous, solving this minimization problem is not trivial anymore. Because in general, Q is going to be a non-convex function. And so finding the minimum of a non-convex function is a very hard problem. And maybe you can even hope you're able to do it, but it's going to take a lot of time. And so that's going to slow down immensely your reinforcement learning method. So dealing with continuous actions with value-based methods is challenging. It's not impossible, people have done it, but it's very challenging. Instead, if we switch to these policy-based methods, we don't need to overcome that issue because we don't have any action value function, we just learn the policy. And also another advantage, which is less obvious, is that in policy-based method, we directly optimize what we care about, which is the average performance of the policy for the environment we want to control. Instead, with the value-based methods, we were not directly optimizing that. Also, with these policy-based methods, we have stochastic policies, which present some advantages. Well, they have to be differentiable with respect to the parameter, of course, because we want to use gradient descent, so they must be differentiable. but neural networks always are. The action probability changes smoothly as a function of the learned parameter, of course. And they enable the selection of action with arbitrary probabilities. So if you have an environment where the optimal policy is stochastic, like if you're trying to learn an agent to play poker, in that case, the optimal behavior is stochastic, it's not deterministic, because you want to introduce things like bluffing, and that works only if you're stochastic. Then you can learn a policy that does that learns to behave in a stochastic way. And in case instead what you want to learn is a deterministic policy, well, that's not a problem, because during training, the algorithm can decide to let the standard deviation of the policy go towards 0. And so at the end, at convergence, you're going to have a policy which is very close to deterministic. Because of course, when the standard deviation becomes very small, you're basically deterministic. Also, another advantage is that sometimes the policy function pi is actually much simpler than the action value function. And so if your method is simply trying to learn the policy, it might have an easier problem to solve than a method that tries to learn the value. That really depends on the specific problem you're trying to solve, and it's hard to know in general. But in practice, this was shown that sometimes it's the case. Okay, all the main policy gradient methods rely on a theorem which is called the policy gradient theorem. And I think it's important that we go through the mathematical derivation of this theorem, because it's not very complex, and it gives us lots of insight into how these methods work and why they are different from the value-based methods that we have seen so far. So the next few slides are going to be devoted to stating the theorem and showing you how you can prove the theorem. So let's first formalize the problem that we are trying to solve from a mathematical standpoint. We define a trajectory with the letter tau. I know that typically tau in robotics is the joint torques, but in reinforcement learning, they use tau for the trajectory sometimes. So a trajectory, what is that? It's a sequence of states and action. Okay, so you have state 0, action 0, then state 1, action 1, state 2, action 2, and so on until the end of your episode.
So this actual now is still discretized.
Time is still discretized. Yeah, time is always discrete in reinforcement learning. Then, given a trajectory, this trajectory has a cost, which is simply the summation of the cost for each time step in this trajectory. And the policy, we're going to call it pi with index theta, where theta are the parameters of the policy which we want to optimize. The objective function, we're going to call it j, which is a function of theta. And j, you can see it here, is the expectation over the cost to go for each trajectory that you obtain when applying policy pi. So of course, depending on the policy, you're going to see different trajectories with different probabilities. And what you want to optimize is the expectation of the cost for this probability distribution over trajectories, which is induced by the policy. And we can imagine approximating this expectation if we had like a finite number of possible trajectories with a summation, where what we are trying to optimize is the cost associated to each trajectory times the probability of that trajectory under policy pi theta. So in theory, this expectation should be an integral because you have a continuous space of possible trajectories, but you can imagine approximating that with a summation if you have like a finite number of possible trajectories. And a possible way to solve this problem, since it's a minimization problem, is to use gradient descent. So we could simply update the parameter theta by following the negative gradient of the cost. So if we are able to compute the gradient of this object here, then we are good. We have a method to solve the problem. It's an iterative method. It may be computationally heavy. We can discuss later about that. But if we have the gradient of that cost, we have a method to solve the problem, at least to find a local solution, because that's what gradient descent does. So our objective for the next half an hour is going to be figure out how we can compute the gradient of this. First of all, before going into the math, what do you think is going to be the challenge here to compute this gradient?
The cost function is not quadratic or convex, and that's why we.
Yeah, I mean the cost can be anything. Let's imagine the cost is differentiable, just to make our life a bit easier. So if the cost is differentiable, then you can differentiate it. I mean, derivatives are relatively easy to compute.
See that it's the global optimum, could also be a local optimum.
That's a problem of gradient descent. It's not a problem of computing the gradient. So it's another level of problem.
Yeah.
And that, by the way, we are not gonna solve it. So this is a local method, as everything we are doing in this course. Everything is local. We don't have any global. We only have global proofs for tabular environments. So when we have discrete states and action spaces, there we have global convergence guarantees. But as soon as you switch to continuous spaces, everything becomes local. And we are cool with that. We accept it. Now, here, the problem is that this probability here, it's a complex object to compute, and it's going to depend on the dynamics of the environment. The probability of visiting certain states, certain trajectories. And in general, in reinforcement learning, the assumption is that we don't know the dynamics of the environment. So we cannot compute that probability in like closed form. And so intuitions would suggest that we cannot compute its gradient. So that at first sight, it should seem like something that cannot be done. Then, of course, I'm going to show you that it can be done. But it's not trivial at all, the fact that it can be done. Okay, so let's take the definition of J, which is this object, and let's take its gradient. So we just add the gradient symbol nabla in front of it. So we're taking the gradient with respect to theta, which are the parameters of the policy. We can swap the gradient and the summation. So we get the summation over all possible trajectories of this gradient. And the problem, as I anticipated a moment ago, is that this probability is very hard to compute directly, as it depends on the dynamics of the environment and also on the policy, because of course the policy affects the probability of visiting a state more than another. And so it's going to be potentially very difficult to do that. So let's try to see how we can achieve this computation, even if it seems impossible at first sight. So this trick that we're going to use to make this computation tractable is called the likelihood ratio trick, also called the reinforce trick. Reinforce is the name of the algorithm we're going to get to at the end of this derivation of the policy gradient theorem. That's why it's called the reinforce trick. So we take the equation we had in the previous slide, and we simply multiply it by the probability of tau divided by the probability of tau, which is 1, of course. So we can do a multiplication by 1 and nothing changes. So we have this p tau here and this division by p tau here. And now what we're going to do is that we're going to exploit the fact that the gradient of the logarithm of x, we know that it's the gradient of x divided by x. And that's exactly the form that we have here. So we have the gradient of p divided by p. We know that we can rewrite that as the gradient of log p. And so this expression becomes this expression, where now I have the gradient of log p instead of the gradient of p. And now I should recognize that this summation here, I can rewrite it as an expectation because I'm simply multiplying this object here times the probability of tau. And so that's simply an expectation with respect to tau. I'm basically going back to the original form where this is written down as an expectation. And so I can rewrite it like this. So I have an expectation where instead of taking the gradient of p, now I take the gradient of log p. And that's going to be the key for making that computation feasible. Okay, we're going to go to that later. Let's try to get to the end of the math. So a trajectory tau is defined by a sequence state control cost over your episode horizon. So we can write the probability of a trajectory as the product of the probability of visiting state xt plus 1, starting from state xt and applying action u, times the probability of choosing that action u while being at state xt. So this is a way to decompose the probability of the whole trajectory as product of probabilities of single transitions from time t to times t plus 1, and also probabilities of taking the specific action that was chosen during that episode while being at that specific state. So the overall probability of a trajectory, you can compute it by multiplying this sequence of probabilities for every time step. And you have like two probability distribution that affect the probability of a trajectory. One is the probability of the policy because that's stochastic. And the second is the probability of the transition dynamics, which again can be stochastic in general in RL. Of course, if we were in a deterministic setting, these probabilities would be 0 for most choices of x and u, and they would be like constants for anything that is not 0 probability. Actually, they would be 1 for the trajectories that have non-zero probability. But in general, we are in a stochastic setting, so these probabilities can take any value, and there are going to be some trajectories that have a higher probability of being visited and other trajectories that have a smaller probability. So once we have written down this definition of the probability of a trajectory, now we can try to compute the term that we had in the previous slide, which was the gradient of the log of this probability. So we apply the gradient and the log, so gradient of log probability, and now you're going to see why the log is key to making this tractable, because now we have the log of a product, and we know that the log of a product is equal to the summation of the logs. And so we can rewrite this as the gradient of the summation of the logs probabilities. So we have one summation for the probabilities of the transitions and one summation for the log probabilities of the policy. So why is this helping us? Because the tricky part is this one, the probability of the system dynamics, because that's the part we don't know. This part here, we know it. That's our policy. We can parameterize it with a neural network. We know exactly the neural network. We can take derivatives of the neural network. That's not a problem. But this one, we don't know it. So that's the part that is giving us troubles. So we cannot compute directly the gradient of P because we don't know this part. Why is this gradient of log P better? Because we still have P here. You can separate, yeah. So this you can say, write it as the gradient of this part plus the gradient of the second part. Sure, you can do that, but still, this part you don't know. What is the gradient with respect to? On theta. The gradient is with respect to theta, and this part here does not depend on theta. And so actually you can just remove it. And so what you're left with is only the gradient of this part, which you know. And that's the basic trick. So that's exactly what we are going to do in the next slide. Basically, we can rewrite the gradient of log P of tau as simply the gradient of this summation of log pi. And now we can move the gradient inside the summation. So we have the summation of gradient of log pi. And so we managed to compute this probability without requiring any knowledge of the environment dynamics, which is exactly what we needed. It's almost magical, this policy gradient theorem. Because we start from an object that we cannot compute, and we are able to compute the gradient of this object. So we don't know the object, but we have a way to get the gradient of it, which is a bit counterintuitive. So yeah, the key property is that the environment dynamics model is not required. Because this is the expression that we need to compute, and it only depends on our policy. So we just need to make sure that we parameterize our policy with something that we compute the gradient of. So a neural network works fine.
Estimate. Like a quick question. I mean, the key point was that we use the Markov assumption basically.
Yeah, we have the Markov assumption here.
Yes. But that is basically the key point. You know, we're replacing our probability of tau given eta with our policy that we
No, I mean, here we replace P of tau with this multiplication of probabilities.
Yes.
But that's always the case when you have a Markovian system.
Yeah, but the logarithm is just I'm there to make it nice because we have the sum instead of the product.
Yeah. I mean, if you try to take the gradient of this, the gradient of a product is not the product of the gradients. And so you don't manage to get rid of the gradient of P. Instead, when you switch to the sum, the gradient of the sum is equal to the sum of the gradients, and then you get rid of P because of that. So this switching from products to sum is key to getting rid of this term here. And the Markov assumption, I mean, here I'm explicitly mentioning it, but it's always been there since day one of this class. I mean, we are always assuming we have a Markovian system. Okay, because that's basically what our dynamics modeling assume. X of t plus 1 is a function of x of t and u of t. It doesn't depend on previous states before t. That's basically the Markovian assumption.
And it works because the logarithm is a monotone function, and that's why we still can, if we minimize the logarithm of our
yeah, I mean, the log is monotone, but actually we are not using that property of the log. Simply, we managed to express our gradient with the log inside by doing this like 3 steps.
Also, we're still using the gradient of j, which is not the logarithm.
Okay. Yeah. I mean, what we are computing is the original object, which is the gradient of j. We didn't switch to the gradient of log j, but we simply managed to make the log appear by using this likelihood ratio trick, basically. So we multiply times p divided by p, which is 1. And then this guy here, we recognize that's the gradient of the log. And that's how the log appears.
Yeah.
So it's exactly the same object we started from. But we managed to remove the dependency on the environment dynamics. It's magical. Yeah, it's magical. I told you. It's magical, but it's 100% correct. We are not making any approximation. It's just good math. You can go through it maybe 3 or 4 times and persuade yourself that it's correct. Okay, so now that we have this expression for gradient of log p, we can substitute it back into the expression for the gradient of j, which was our cost. And we get this. So the gradient of our objective function is an expectation over trajectories of this guy here, where we have the cost of a trajectory pre-multiplied by the summation of the gradient of the log probability for every action and state that we have visited during that trajectory. Yeah. So the gradient of the cost function that we are trying to minimize. So this cost function, remember, it's the expected cost over all possible trajectories, is the expectation over all possible trajectories, assuming we are using the current policy to act in the environment. And what we have inside the expectation is a product. So this term here is simply the cost of a given trajectory. And instead, this term here is the summation of the gradient of the log probability of the actions that were taken given the states that were visited. Seems very abstract. Now we're going to try to interpret it. But first of all, how do we deal with this expectation? Because an expectation is an integral over a probability density function, which we don't know, because this is an integral over the PDF of the trajectories, which was this complex object we don't know, the P of tau. Well, we simply sample. So, and that's basically everything we have been doing so far in reinforcement learning. We need to compute expectations, we sample. We can do Monte Carlo sampling. So you simply run your current policy for a certain number of trajectories, let's say M trajectories. And then you compute that expectation simply as an average over these M trajectories. So instead of having this expectation here, you're going to have a summation over all the trajectories, and then you're going to take the average value by dividing by M. So this is a Monte Carlo approximation of an expectation. It's extremely simple. And that's the same we did when we wanted to do policy evaluation. We could do it with the Monte Carlo method. Well, that's exactly the same idea. And this is basically the starting point for the reinforced algorithm, which is like the starting point for all policy gradient methods. It basically computes the policy gradient using this expression here, and then it does gradient descent to optimize the parameter theta. So you can see that as a Monte Carlo policy gradient method, because it uses Monte Carlo to estimate the policy gradient. Yeah, this is a gradient expectation. And as I was mentioning a moment ago, then you do gradient descent. So you simply take that object and you use it as your gradient to update the parameter theta. So for every trajectory, you update the parameters of the policy pi, sorry, the parameter theta by taking a step in this direction. So you have the cost to go, and here you have the gradient of log pi. Let's try to think a moment about what we are actually doing when we use this gradient estimation. So what we are doing is that here, this pi is a probability measure, okay? And it tells you how likely it is to take action U when you are in state X. And what we are doing is that, well, we're taking the log, but the log is a monotone function, as you were pointing out before. So the log doesn't change the trend of the function we are taking the log of. So you can forget about the log for a second. And then we are taking the gradient of that probability. So this gradient of the probability tells us in which direction you need to change theta to make the probability increase. Okay, so gradient of the probability, it is what's the direction in theta space to make the probability of that action at that state go higher. And then you're moving, you're scaling it by the cost. Okay, so imagine that the cost was very good for that episode. So you have a negative cost, minus 1,000. With a minus in front, it becomes plus 1,000. So you're moving your parameters, theta, in a direction that makes the probability of that action higher. So if you had a negative cost, you make the probability of that action higher. If instead you have a positive cost, so opposite sign, and a positive cost is bad, you're going to do the opposite. You're going to make the probability of that action lower. Okay, so what this update rule is doing is actually very intuitive. It's looking at the cost over the episode. If that episode had a positive cost, I want to decrease the probability of the action that I've taken because a positive cost is bad. If I had a negative cost, that's good. And so I want to increase the probability of those actions. And I'm going to do this increase and decrease proportionally to the cost. So if I have a negative cost minus 10 in one case and in another minus 20, then minus 20 is better than minus 10. And so I'm going to increase more the probability of the actions that I've chosen during the episodes that had the best cost. Yeah.
So you're using the logarithm, and the logarithm is monotone, but it's not linear.
It's not linear, no.
Do we change the speed of our updating, basically? Because
yeah, so to be
for higher pi of u t with nice and theta.
Yeah, so basically everything I've told you is actually true if you replace probability with log probability. And that's actually what's written down there. It increases the log probability, but just to simplify my speech, I simply switch to probability.
Sorry.
No problem, no problem. Okay, so just to repeat, the update moves theta, so the parameters of the policy, in the direction that increases the log probability of the action ut that was taken in a way that's proportional to the negative cost to go ct. So if ct is negative, the probability of ut is increased. If ct is positive, the probability is decreased in a way that's nonlinear because there is a log in between. So another way to analyze it is that this gradient tries to increase the probability of path, so trajectories, with negative cost to go, and decrease the probability of path with positive cost to go. So this is a very simple way of interpreting it. It's also a bit misleading because it seems that the sign of the cost plays a critical role. And that's not how typically optimization methods work. So if you add a constant to your cost, that shouldn't change the result of the problem, right? And here instead, it seems that the sign is what matters in making increase or decrease the probability. And I mean, this is how you find this gradient explained in the literature. But what's going on is a bit more complex. So you could have a cost function, for instance, that is always positive, and this would still work. And the reason why this would still work is that you would have still small positive cost for like good trajectories and high positive cost for bad trajectories. And this would result in trying to decrease the probability of all actions because the cost is always positive. But since the probability of all actions for a given state must sum to 1, and that's typically implicitly guaranteed by your PDF parametrization, which is going to be an exponential if you use a Gaussian, which is the most common choice, then you're going to try to decrease some probabilities in a way that is stronger than others. And so what's going to happen is that the probabilities that you try to decrease a lot because they have a very positive cost, they're actually going to decrease, but decreasing at a certain point is going to make everything else increase because the integral of your PDF must always be 1. Okay, so this works even if the costs are always positive or always negative, because we have this implicit constraint that the sum of probabilities of all the actions for a given state must be always 1. Okay, you can imagine you have your Gaussian PDF, and so this is the space of U, and you have chosen some value here, ut, and you try to decrease this probability. So you can imagine like you're pushing down on that point of this Gaussian, and yeah, you can push down there, but if you push down there, then the rest of the PDF should change so that its integral still remains 1. And so maybe after pushing down there, what happens is that it becomes something like that. So you have decreased it here, and you have increased it somewhere else to compensate for it. So even if the cost is always positive or negative, everything is gonna work nicely in the end because the summation must be always 1. So it doesn't matter the absolute value of the cost. What matters is the relative value of the cost of the different trajectories, as in any optimization method. So this is an additional level of understanding of how it works, which is a bit more accurate with respect to the previous explanation that's written in the slide. So let's try now to see more detail how this reinforced algorithm works. So it's a Monte Carlo algorithm. We already said that. It uses the complete cost to go of an episode to do the update of the policy parameters. And the updates, as in all Monte Carlo methods, must be made at the end of the episode because you need to have the complete cost of the episode to compute the policy gradient. So in terms of theoretical properties, it's a stochastic gradient method whose expected update over an episode is in the opposite direction of the cost to go gradient. Okay, it has good theoretical convergence properties, as all Monte Carlo methods. We have seen that they are theoretically more robust than temporal difference methods. So it's you can be sure that you're going to converge to a local optimum under classic conditions for decreasing alpha. So the alpha, which is your step size, it needs to go to 0 eventually if you want to have convergence. Otherwise, it's going to oscillate. So this is a pseudocode of Monte Carlo policy gradient, so reinforce. So as input of the algorithm, you need a differentiable policy parametrization pi, parametrized by theta. And you need to have a value of the step size alpha, which is greater than 0. You initialize the policy parameter theta to whatever value you want. You can, for instance, initialize them to 0. And then you're gonna run episodes for a given amount of time. You generate an episode, which is just a sequence of state, control, cost, state, control, cost until the end. And you do this episode using the current policy pi, which is stochastic. You compute the cost to go of the episode, the total cost to go of the episode. And then for every state that you have visited during the episode, you update the policy using this update law, which is the update law that we have derived with the policy gradient theorem. So you update theta in the opposite direction of the gradient of your cost, scaled by your step size alpha, also called learning rate. And the gradient is simply the total cost of the episode times the gradient of the log probability of the policy, evaluated at the state and controls that were actually used during the policy. Sorry, during the episode. Okay, so it's quite simple. Doesn't take much to implement it. You just need to figure out how you compute this quantity here. That's the only quantity that requires some consideration for the computation. Everything else is quite trivial. But with nowadays library like PyTorch, computing this gradient of the log probability of the policy is quite straightforward because all the difficult part is already implemented in the library. Okay. I think even if it's a bit early, it's been quite intense, this 50 minutes we have done. So let's take a break, 10 minutes. So I'll see you back here at 35. Okay, let's start. Let's discuss now how we can improve on this reinforced method. Because reinforce is correct, meaning that it's an unbiased algorithm because the gradient estimate that it uses is unbiased. So if you sample infinitely many trajectories, you're gonna get the exact gradient. But since it's a Monte Carlo method, we have seen that the problem of Monte Carlo methods is that they have a high variance. And so the gradient estimate that you get is very noisy, which is going to result in slow convergence, slow learning. So it's inefficient. It takes a long time to learn. And it's very noisy in its convergence. So ideally, as we did for Monte Carlo, we're gonna try to find an alternative which reduces the variance. A first little improvement that we can try to apply is by simply exploiting causality. So if you look at the definition, at the way we estimate the gradient, it looks like that. So we have first a summation here over all the trajectories. And then for every trajectory, we have a second summation with respect to the time step of all the state and actions of that trajectory. And we can try to exploit causality. So we know, because our system is a dynamical system, that the actions that you take at time t, they only affect what happens after time t. They don't affect the past. That's pretty straightforward. So how can we exploit that to make this gradient estimates less noisy, with less variance? Let's write down this cost here as a summation, because the cost is simply the summation of the instantaneous cost at each time step for every pair state action. So we simply rewrite this as this. And then here we split this cost into two parts. We have first a summation going from 0 to t minus 1, and then a second summation going from time t to the end of the episode at time capital H. And also I've moved this inside the first summation, because you can see that now this part, which is this, is inside these brackets, which I can do. It doesn't change the final result. Okay, so far I've just rewritten the original expression in a different way, making it more explicit that here I have two components, one that depends on the past and one that depends on present and future. Okay, so what I can observe is that actually this part here of the cost is independent of the action u at time t, because that's the cost before arriving to time t. So whatever action I take at time t, it has no effect on that part of the cost. So on average, that part of the cost is going to be 0. Or better, it's completely independent of the action. So if I use this part of the cost for modifying the probability of that action, on average, that probability is going to be sometimes increased, sometimes decreased, but on average, it's going to remain unchanged because it has no relationship with that. And so actually this part of the cost to go is just adding noise to my gradient estimate. It's unbiased because on average it's not going to affect my probability for that action at that time, but it's just adding noise. So it's making my gradient estimate more noisy. And so I can actually remove this part and I still get an unbiased estimate, but with a smaller variance, just by exploiting causality. So the improved policy gradient is this one, and it looks very similar to the previous one. The only difference is that now for changing the probability of the action I've taken at time t, I'm only going to use the cost starting from that time until the end of the episode instead of the total cost of the whole episode, which makes a lot of sense. Because we know that the action you take at time t has only an effect on the future cost, not on the past cost. So it makes sense that we only use the future cost as an evaluation metric for judging if that action was good or not. So this, of course, was not a mathematically rigorous proof. It's just to give you a bit the intuition of what's going on and why we do that. However, the key point here is that even after we do that, we haven't really solved the issue of high variance. So this trick of exploiting causality it improves a bit the variance, so it reduces it a bit, but it still remains very high. Okay. So it's just a little step in the right direction, but it's not a solution. So if we want to really solve the high variance problem of these policy gradient methods, we need to do something that is a bit more effective. And that's going to be introducing a baseline. So what is a baseline? A baseline is a constant that you subtract from the cost to go that you use in the policy gradient estimation. So it's this B term that we are introducing there, which I said it's a constant. It's a constant in the sense that it's independent of the action U. It can depend on the state, however, X. So it's more correct to say that it's a function of the state. It can also be, of course, a constant, because that's a special case of being a function of the state. So what we can show is that if you modify the policy gradient estimate in this way by introducing this baseline that you subtract from the cost to go, you still get an unbiased estimate of the policy gradient, which is, of course, not obvious. And then why is it interesting to do that? Well, because if you choose wisely this baseline, you can reduce the variance of the policy gradient estimate. So we can solve the problem of high variance by means of this baseline. And then we will see also that at an intuitive level, this baseline can make a lot of sense. It's a little trip, so bear with me. So this is a generalized version of the policy gradient theorem with the introduced baseline. And it remains valid if and only if the baseline does not vary with the action U. So the baseline can depend on the state, but not on the action. Yeah.
Why it is called the term CT minus the baseline effective cost to go?
It's the effective because it's the one that you actually use. Effective in the sense it's the one that is used in reality, in practice. Maybe we could call it the actual cost to go, if you prefer.
But now we are subtracting by a term, and so it's like an artifact.
An artifact.
Yes. Our goal is to lower the variance.
Yeah.
And so I subtract by a term that is tuned over to lowering the variance, and so it's obvious.
It's obvious that you can decrease the variance.
Yes.
It's not so obvious to me.
So this term is added for this goal. So
it's added for the goal of reducing the variance, but we need to prove two things. First, adding this term does not alter the soundness of your policy gradient estimate. So you're not introducing a bias in your policy gradient estimate. So you still have the properties that if you take an infinite amount of samples, so you do infinitely many episodes, the policy gradient estimate converges to the real gradient. That's the first property we want to show, and that's what I'm going to show, I think, in the next slide. Second, we need to figure out, okay, how do I choose this baseline so that I get a reduction of the variance? Because even that is not obvious to me. I mean, it wasn't before I studied this topic, of course. But I think that for you now, it's not obvious how you choose B so that you reduce the variance. but trust me, there is a very natural choice for B, which makes a lot of sense. And I'm going to give it to you in a couple of slides. But first, we see the concept in this general way of having a baseline, and then we see how we can choose something that makes sense for baseline. Okay, so the baseline, what's important is that it does not depend on the action. It can only depend on the state. And the way we can see is that actually introducing the baseline does not alter the validity. So the fact that it's unbiased, the policy gradient estimate, is by computing this expectation. So we have the expectation of the gradient of the log probability of the trajectory scaled by the baseline, because that's basically the extra term that we are adding in the policy gradients, right? So this new policy gradient, you can see it as the previous policy gradient, which was this, plus an extra term, which is the baseline times this. And if you go back to the slides to see how we derived that expression, well, we started from something that looked like that, where here I'm replacing the cost to go with the baseline, because that's the term we're adding. So if we can show that this expectation here is 0, then we have shown that we are not introducing any bias in our policy gradient estimate. It's quite simple to show that this is 0. You just go from the expectation to the summation scaled by the probability of every trajectory of this term here. Then here you have probability times gradient of the log probability. So since we know the gradient of the log, we can transform this into this expression. We are doing basically the reverse of what we did before with the likelihood ratio trick to introduce the log. Now we did the inverse operation to remove the log from the expression. And now I can move the gradient outside the summation. So I get the gradient of this summation. And since B of x, which is the baseline, is independent of the parameter theta over which we are taking the gradient, this actually I can move it outside the gradient. So it goes here in front of the expression. So you have the baseline times the gradient of the summation of the probability of a trajectory over all possible trajectories. But the summation of the probability of all possible trajectories is 1. Because the summation of the probabilities must be 1. That's a property of any probability density function. And so I'm taking the gradient of a constant, which is of course null. And so this is 0. So the property I have to exploit is this one. Summation of the probabilities over all possible trajectories is 1. So that's a constant. So this proves that introducing the baseline does not introduce a bias. We are still unbiased, which is good. It's a very nice property to have. Now what we need to figure out is, okay, it's not doing any harm because it's not introducing a bias, but is it helping us in some way? Well, it depends on how you choose the baseline, of course. It turns out that a very natural choice for the baseline to use is the value function, which satisfies the property of depending only on the state and not on the control. So if we can use as baseline the value function, of course, it's a value associated to the current policy, then what we get is basically that the cost to go minus the baseline, which is the value function, is called the advantage function. What is the advantage function? It's basically a function that tells me how good this action is with respect to the average cost that my policy would give me starting from this state. Because I'm taking the total cost starting from that episode, from that state until the end of the episode, minus the value, which is the expected cost starting from the state and behaving according to the policy. So now this advantage is much better because this is really going to be positive if this action here, U, is worse than what the policy does on average, and it's going to be negative. Remember that negative for us is good because we are minimizing. Negative if the action is better than what the policy does on average. So now this new term that we are using for deciding whether to increase or decrease the probability of a certain action, it really has a sign that's correlated to how good that action is with respect to what the policy does on average. So in expectation. So the intuition is the following one. The policy probability pi is increased only if the action U yields a cost to go that is better than the expected cost to go V of X. So that's the effect we are getting introducing the value function as a baseline in the policy gradient estimate. So this relative comparison that we are doing, so comparing the cost of the episode with the value of that state, it allows the parameter theta to differentiate between better and worse actions in a state where all returns might be generally high or generally low. So now we are no longer changing the probabilities of actions based directly on the absolute value of the cost, but we are comparing that cost with the average cost starting from that state. So this is as an effect of like normalizing. Yeah.
But why does it make a difference? Because I thought we were maximizing or minimizing anyway. So if we just subtract it, we should get the same result.
Yeah, in expectation, it's true because everything we are doing so far is unbiased.
Yes.
So in expectation, it's all the same. But since we don't not only care about the performance for the number of samples going to infinity, but we also care about performance for a finite number of samples, then there is a difference.
Use BR to decide for each time. Like, didn't we? I need to look this up again before I ask a question. I'm sorry.
No problem, no problem. I mean, I think I get what you mean. They are both correct. It's just that this one is going to be more efficient, so it's going to learn faster because we are basically reducing the variance of the estimate, and we are also normalizing a bit the values because there might be state from which the cost, the total cost to go is generally very high, and other states where that's generally very small. And that introduced like bad scaling in our gradient estimates by instead subtracting this value here, which tells you on average what's the cost from that state. You're removing this scaling issue.
That makes sense. Thank you.
So yeah, empirically, the result is that the algorithm is going to learn much faster. In expectation, it's going to learn the same thing. We are just making it faster. Of course, there is a key issue here, which we haven't discussed, is that this value function, we don't know it. And so we need somehow to estimate it, but that's a problem we have already discussed, right? If you have a policy and you want to learn the value function, you do it. You can do it with temporal difference learning. You can do it with Monte Carlo. That's everything we have been doing basically until today.
I don't get why we did all of this to remove the state value function calculation, and then now we are saying, yeah, we can use the state value function.
No, we didn't do this to remove that. We did this to be able to learn policies that are in continuous space and stochastic. And it happens that to achieve that, the way we decided to do it is by learning directly the policy without the value function. But then it turns out that actually the value function can also help in these kind of methods. And so we are reintroducing the learning of the value function inside the method to improve it. But now the policy is not computed as a minimizer of the action value function. We still have an explicit representation of the policy. So we don't have the issue of value-based methods that to compute the policy, you need to minimize the Q function. Here, the policy is just this Gaussian stochastic policy that we can directly evaluate without the value function. The value function is just used in the policy gradient estimate. And it's a value and not an action value. So it's a different object. So this would be an extension of reinforce with baseline. So with the value function used as a baseline. It's very similar to before, but what we do is that we collect now a batch of trajectories, not a single one. So you do a batch of episodes running the current policy, pi theta. For each time step, you calculate the total discounted cost to go and the advantage function, which is this difference between the cost starting from the state until the end of the episode minus the value function associated to that state. Then you refit the baseline, so the value function, by trying to basically predict the cost that you have seen in the episode with your neural network, because that's what we do if you want to do Monte Carlo value estimation. And then you update the policy using the policy gradient estimate, which is the usual one, but using the advantage instead of the cost to go. That's it. So the key difference is that now we have basically two neural networks, one representing the policy, one representing the value function. So at each iteration of the algorithm, we need to do two updates, an update of the policy and an update of the value function network. So this was still an unbiased policy gradient method. But if you want to improve things even more, you need to accept a bit of bias, like we did for value-based methods. At a certain point, we switched to temporal difference, and we accepted that with temporal difference, we have some bias. But in exchange for this bias, we actually reduce a lot of variance, and so we get faster convergence, which is in the end what we care about. Well, the same line of thought can also be applied here to these policy-based methods. We can switch from Monte Carlo to like temporal difference principles, accepting that we're going to introduce some bias, but in exchange for a smaller variance and so faster learning. And that gives what are called actor-critic policy gradient methods. So the idea is to achieve online incremental learning, and further reduce variance by introducing bootstrapping. And bootstrapping, if you remember, is this key principle behind temporal difference learning, which is that you use your current estimate of the value to compute the target that you want to fit with your value function approximator. So we're going to have two networks, one representing the actor, pi, and one representing the critic, v, which is the learned value function that evaluates the current policy. The trade-off is that we introduce bootstrapping to reduce the variance, but we also introduce a bias. So we need to be careful because if not tuned properly, this bias may actually jeopardize completely the convergence of the algorithm because it's leading you elsewhere. So how do we do that? Well, so far we have used the complete cost to go in the gradient estimate. We can simply replace the complete cost to go with a one-step prediction of the cost to go based on the current value approximation. Same principle that we applied when introducing temporal difference learning a couple of weeks ago. So this is going to be the one-step advantage estimate. So before, this guy here was the complete cost to go, CT. Now, instead of having the complete cost to go, we just take the instantaneous cost for the current time. And then everything after that, we replace it with the current estimate of the value function. So we have the value function here evaluated at the next state. Why is this better? I mean, to a certain extent. Do you see it? So the cost to go would be L of, well, this should be L of t, not t plus 1, L of t plus discount L of t plus 1 plus discount square L of t plus 2, and so on until the end. Why is it better to use the one-step prediction than the real thing? What's the advantage of the one-step prediction? Nobody?
Maybe with an estimate, I'm using a stochastic policy, and I'm using a stochastic policy, so it's already an average of the possible value function, not deterministic.
Yeah, you're close. So what happens if you start from state xt and you run the policy, your current policy, once? You get a certain cost. What happens if you repeat this process a second time? Do you get the same cost? No. every time you repeat that process, you're going to get a different cost. Okay. And that has potentially a very high variance, because if your episode is long, you're taking many steps. At each step, there is stochasticity involved in the dynamics, in the policy. And so if you use this estimate, it's going to be very different every time you pass through that state, which means that it's very stochastic, it's very high variance. What about this estimate here? Of course, you have variance here because the current action is stochastic, and you have variance in the next state because that depends on the stochasticity of the environment at time step t, but that's it. You have only these two sources of stochasticity, the policy at time t and the environment dynamics at time t. So stochasticity is very, very much reduced now. So you're still going to get different values every time you visit that state, but the variance is going to be small. In the other case, you have the stochasticity of dynamics and policy at time t, the stochasticity of dynamics and policy at time t plus 1, stochasticity of dynamics and policy at time t plus 2. So you have many sources of stochasticity, which you're getting rid of. The problem, of course, is that this value is an estimate, so it's not correct. If it was correct, this would be a superior choice, period. It's not exact, this value, it's an estimate. So you're, yes, reducing the variance, but you're introducing a bias, which is your function approximation error of the value function. And that's the trade-off we are working with. So this was what we were calling before the advantage function. Now it's when you replace the total cost to go with this one-step prediction, instead of the advantage, you end up having the TD error. If you remember, this was exactly the definition of the TD error that we used when we introduced temporal difference learning. So we got to it in a completely different way, but now we can recognize that it's the same guy. So when you update the policy, you're going to do it using always the gradient of the log probability of the policy. But the scaling that you're going to have in front of it is not going to be the cost to go, is not going to be the advantage, it's going to be the TD error. And then, of course, you always need to learn the value function because that's not given. So you have to learn it at every iteration of the algorithm. And also that learning is going to be guided by the TD error, as usual. This is not something new. So now we have an algorithm that is fully online and incremental, so we can update at every step of every episode. We don't need to wait until the end of the episode to compute this cost to go. We can do it at every step. And this is a pseudocode for how this algorithm could be implemented. So for every episode, you initialize the state to a random value. You take this I value that's initialized to 1. It's going to be called eligibility trace factor. You do a loop for the episode length until you reach the terminal state. At every time step of the episode, you pick some actions using the policy, you sample from the policy. You take the action U in the environment, which gives you the next state and the cost. You compute the TD error delta, which is simply the cost plus discount factor times your estimate of the value function at the next state minus your estimate of the value at the current state. You update the critic by following the gradient of the critic network scaled by the TD error delta. And then you update the actor by following the gradient of the log probability of the policy scaled by delta and also pre-multiplied by this I value, which is there just to take into account discounting. So as you move on during the episode, you have discounting for the cost. Well, you can also decide not to have it. If you set it to 1, then it's just, you can remove it. But if you have discounting, then this I is multiplied by gamma at every iteration of your episode, so that here you have discounting. And then you update the current state and you repeat. So this is how you could implement one of these methods. And then there are more advanced versions, which we don't have really time to cover today because we are almost out of time, but I'm gonna mention them very briefly just to give you an overview of what's in the state of the art. So if you do one step TD error, we know that we reduce a lot the variance for the reason we discussed a moment ago. You just have the variance coming from this one step of experience. But you have possibly a high bias because your value function estimate may be highly biased. With Monte Carlo, we were at the other extreme of the spectrum. We had high variance, but actually no bias at all. You can think of doing something in between these two extremes. So there are these methods which are called generalized advantage estimation, which use an exponentially weighted average of multi-step TD errors. So these are TD errors where instead of just looking at one step of experience and then replacing everything else with the value function, you look at multiple steps of experience, and then you truncate that computation of the cost and you replace the tail with the value function. It's something in between Monte Carlo and temporal difference learning with just one step prediction. And so you can get a good balance between bias and variance. Then you have this method called asynchronous advantage actor-critic, A3C, which uses n-step advantage estimation with bootstrapping. And then you have more state-of-the-art method like TRPO, which is trust region policy optimization, and PPO, which is still nowadays used in many robotics applications. So this is really state-of-the-art, which introduce constraints to stabilize large gradient steps. These are mainly regularization techniques that have been added to the standard policy gradient methods, which are helping a lot in making the learning happen fast and in a more stable way. But the core mathematical concepts have remained the same that we have discussed today. So if you understand well reinforce and its first two extensions we have discussed, so with the introduction, with the exploiting of causality for removing the dependence on past rewards, and the introduction of the baseline, which is the value function. That's the key principle behind state-of-the-art policy gradient methods such as PPO, which is proximal policy optimization. Then, of course, if you really want to understand state-of-the-art methods, you need to go through the papers and understand the extra tricks that they had to add to make this method more robust and scalable and efficient. but in terms of math, most of the complexity, we went through it today. So we got to the end of the lecture. Let's try to summarize the key concepts. So moving from value-based to policy-based method, we can directly optimize the policy by trying to minimize this performance matrix J, which was the expected cost under the policy pi. And we minimize it with respect to the parameters theta of the policy. That is continuous, that is compatible with continuous action. So finally, we can optimize policies that outputs are continuous actions and not a discrete one. We have seen how these methods are based on this theoretical result called policy gradient theorem, which provides a theoretical foundation guaranteeing that a gradient can be estimated from samples without knowing the model, which was not obvious by looking at the problem at first sight. Once we have the policy gradient theorem in our hand, it's pretty obvious to derive the reinforced algorithm, which exploits this theorem to estimate the gradient and updates the policy parameters following the negative gradient direction. The problem is that while it is unbiased, this reinforced algorithm suffers from high variance. And so people started looking into how they could improve. And the main source of improvement comes from introducing a baseline into the policy gradient. So instead of using the cost to go, the complete cost to go, you subtract from the cost to go a baseline, which can depend on the state. And it turns out that a very valid choice for this baseline is the value function. So we can introduce also a value function estimation inside our algorithm, and we can use this value function as a baseline inside the policy gradient estimate to reduce the variance and so makes the learning more efficient. If you want to improve, to accelerate learning even more, you can do that by switching to actor-critic methods, which instead of using the complete cost to go, they replace it with a one-step or multi-step estimate, which is based again on an estimation of the value function. But at that point, you're also introducing a bias. So it's a trade-off. But that's what modern RL methods do. So in practice, that seems to be the best option. So in robotics, this policy gradient method actually have had a lot of success. They've been applied to solve many problems. Actually, I would say that they're the most commonly used for robotics application, especially PPO is very, very widely used in robotics and not only in robotics. Even if they're not the most efficient methods in terms of sample efficiency, they are very stable, so they're relatively easy to make converge, and they can be parallelized very easily. So nowadays, with very powerful GPUs, even if they're not the most efficient, people don't care because they can just attack it with a brute force high-power GPU, parallelizing a lot, so collecting lots of samples in parallel. And so in the end, what you get is that you can train your policy in a matter of minutes or, well, hours if it's more complex. So they can handle continuous controls. They've been applied a lot to solve locomotion problems for like quadrupeds or bipeds doing locomotion, trained in simulation, and then deployed on the real system with direct deployment with no fine-tuning on the real system. So that's been a lot of success. Or they've been applied also to helicopter to do acrobatic maneuvers on helicopters. And they provide a very valid alternative over more classic action-based methods that we have seen so far, like deep Q network. And I think that's it. So we're even 7 minutes in advance. Do you have any question before we wrap it up? Okay. I know it's a lot to digest. I've been through it a few years ago, so I still remember the struggle. So don't worry if you feel overwhelmed by all the material we have covered today. It's, I think, completely normal. Just take your time to go through it, digest it, and I think it's gonna feel better after a while. So we have one lesson left, which is gonna be next Friday. Remember, especially for the foreigners, on Monday it's bank holiday, so university is closed. And next Friday, we are gonna just do a summary of everything we have seen in this course, trying also to draw some connections between the different methods we have discussed, to compare them and discuss in which case it's more appropriate to go towards one class of methods more than another. And then I'm gonna give you the final project instructions so that you can start working on the final project. And I'm gonna describe a bit how the oral exam is going to work, especially if you've never taken an oral exam in Italy. I've learned that it's better to warn students of how that's going to play, because some people from other countries don't have that kind of exams. And so when they arrive at the oral exam, they are a bit confused. So we will try to do all of that next Friday. I'll see you in a week.